All right, very good. I do have a poster, and you can ask questions, and we can cover more items there. What I do want to cover is the kind of key ingredients, right? So I'm going to go through pretty fast. The title is a little bit changed from what's in the agenda, but I think this captures the ideas that I'm trying to present to you. It's about adaptivity in terms of architecture and using bit precision as a way to regulate learning. It is not about hardware. It's a little bit about algorithm, but it covers a little bit of both. So one thing I want to start with is talk about applications and how that drives some of the requirements and some of the thinking that goes into using bit precision. And we'll get to that. So within SRI, as a nonprofit, we do a lot of different research in sensing, robot autonomy, those kind of things, medical imaging, all those kind of things that deals with the environment. I'll call that traditional applications. We also have other applications where we actually look at the processors themselves. There's a lot of signal that come out of the processors like high performance counter, cache behavior kind of thing. We're extracting those signals and using a learning model to say, well, can we build a better branch predictor? Can we build other control mechanisms given the information in the processor, right? And perhaps this is something that Bob Caldwell will talk about. You know, these are the transitional kind of things where we can start to replace some of the mechanisms within the processor. We're also looking at applications where we take functions and replacing them with neural approximations, right? As a substitute, perhaps, Loihi will be part of something, as even Brad have said, replacing functions with kind of neuromorphic kind of equivalents. So we're looking into that. The talk itself is not about all these applications and systems, but it drives some of the requirements. What we would say from all these kind of things is that there is a need to sense, learn from it, right, and then react to the adaptivity as part of it. Now, to drive a little bit more concrete details about it is, let's give it an example, an imagery, where you train upon a set of data. You know, it might be good lighting conditions, and then in the environment, you're going to have very dark or high lighting kind of sun in the background. We've been through all that, right? So these robotic systems encounter this in the field. How do you adapt to that kind of situation? This is just but one example. And folks have talked about some sort of approach with transfer learning, domain adaptation. Those are all possible. Our approach in this presentation context is say, what if we trigger and then select a new model? Let's say, for example, you have a neural model that's trained on something that's green. You suddenly see a shift in the data that you now need to switch to a different model that's trained on blue, right? So this kind of nominal architecture, right? This doesn't have to be the set for you, but it gives an example of what we're talking about, that you need to detect this kind of drift, you need to select a new model, and then you go on and work in that model and continue learning in that. So this talk is not about the detection of drift. There's many different ways to do it. It's not about the learning itself. Folks have talked about spiking models and all that. But it's about the model selection, right? How do we know which model to go to? And in particular, trying to select a new model without training to convergence. We know that it takes some time, right? At least with the classical kind of deep networks, it takes a lot of time. It's about then saying, within the meta-learning kind of context, how do we train it? And in particular, in this presentation, using bit precision as a way to guide the learning. Now, shifting gears and say, okay, low bit precision, what have people done with respect to things in the field? There's very simple approaches about, I'm just going to truncate my precision here. You know, take an example like 3.14, and you might cut it down and say, that's good enough. And now I have mapped some sort of precision, either from floating point to 8-bit or 8-bit down to single bit. It's been done. And people have talked about pruning. You have a lot of synaptic connections, and maybe some of them are not as important. But fundamentally, something is lost there, right? You kind of throw things away. Even though you might do it over different epochs, it takes time in terms of the iteration, and somehow you are forgetting something when you truncate it. Now, people have looked at other approaches in terms of training it down to single bits. Now you're forcing it to come to and arrive at a neural network that is a single bit, but itself is also kind of restrictive in a way. So what we suppose is, well, maybe let the bit precision itself be a free-floating parameter. as part of the loss function. Right? What happens if you allow the neural network to train with that flexibility? Right? Will it arrive at a conclusion that maybe this particular layer needs 8 bits or 4 bits, and those kind of things? So to achieve that, we actually go into the loss function and added kind of parameters that allows the training function itself to consider optimality from a respect of both the loss, performance loss, and also a penalty from the bit precision itself. Therefore, it kind of thinks about, well, should I add more bits? Will it get me better? And kind of continue towards that. So in other words, it's free-forming. It's no longer mapping to any single bit or 8-bit. It's not all homogeneous. And we're not kind of throwing things away from a perspective of pruning or kind of rounding, right? So the key here, and there's a paper on arXiv that you can look at, where we looked at the mapping these functions into gradient descent kind of algorithm backprop that we use. The key there is a need to maintain some smoothness in the loss function, because you need to kind of do gradients calculations over there. But I'll skip that for this slide. Now we want to get to the results. So this is a very easy example on CFAR, Linnet 5, simple architecture, but it kind of gives the idea that for any network in there, allowing the network itself to kind of consider what should be an appropriate set of bits per layer, you arrive at this solution, right, for CFAR 10, for example. And what we talked about here is the compression notion, right? How much bits did you save if you go into that? So for this example, about 6x, where we let each layer decide how many bits it ought to have at that particular hierarchy, right? So that's the kind of easy answer in terms of, oh, do we have any bit savings? Well, we know we can go down from floating point to 8 bits and so on and so forth. So in this case, 6 bits. So that's one particular result. But I think the more important result that I want to point to is how it's learning, right? So here's an example where we show a comparison with very kind of naive k-means to maybe more sophisticated Bayesian models, maybe traditional gradient descent kind of thing, and then with this bit ability to kind of manipulate the bit for guiding. So the lower is better in terms of test error, and the green line at the bottom shows how it would converge faster, right, down to the knee of the curve there, right? So actually you can, in this case here, where you allow the bit precision as part of your loss function, you're now cranking the learning rate a little bit higher. You can actually force it to say, learn faster. So that's, I think, is a key finding that I want to share. And then if you just kind of take a snapshot of it, and I want to highlight this a little bit more, I talked about the BitNet having a small memory footprint. That's understandable. We understand that there is ability to kind of gain down even the single bit. But most important is the ability to then drive the learning curve, right? And kind of increase the learning rate. And it actually converges down, I think, at a certain point. Certainly, if you take the traditional approach, you can eventually get to the plateau performance, but it's about getting there faster. So from an adaptive architecture perspective, this is important. You're actually getting to where you want to get to without training for a long time. And you can then think about model selection and then moving on from there. So in summary, and this is my last slide, what is the principle about this, right? Does it really work? And I think right at this point, it's still being observed, right? We do know that higher precision, if you give it the freedom, let's say a 32-bit floating point, if you give it the freedom in terms of the training perspective, there's a room to oscillate, right? There's a lot of room that you can wiggle around. Therefore, it takes a longer time to converge. But if you use bit precision as a way to regulate that, right? Force it to say, you only have 5 bits or 6 bits, it actually now trains a little harder and get to the right solution that you want. So that's what intuitively we think. Then we can think about extensions, right? Where does this go? Bit precision in itself is a physical constraint. We're tying it to performance from a learning perspective. what other things could there be, right? In terms of power, perhaps, or signaling communication, spiking or not. We can think about that. And think future work, we're now looking at more complex networks. And what we show is very simple in a way, deeper networks, recurrent networks, and how would they work. And I think the other thing that we're going to try is say, OK, what if you go the other spectrum, where the networks themselves have complex weights, and then give it the freedom itself? Do we observe the same principle or not? So I'll be glad to talk about this more at the poster session. I'll just leave it at that for now. Thank you.